Here is our first experiment, the critical speed of the shaft. Here you can see the revolution machine. It's the revolution RPM machine from which it provides rotational motion to the shaft. This is our motor. Provide the revolutional motion. The motion is transferred to the bell pulley system. Here is the bell mechanism. So this the motion transfers to the shaft. Here is our shaft. It is supported by bearing at the two ends of the shaft. There are two bearing. It's fixed at the two end points of the shaft. This made the shaft a simply supported beam. For this bearing support, this is the guide van, which we can move to and fro, and the mass also can be moved. The mass also can move along with the guide van. The guide van is here to protect ourselves from the high vibrations or an accident occurs. First of all, we need to measure the diameter of the shaft. So we'll take three different readings from three parts of the shaft, and then we average the values. It's around 6 millimeter. We are taking three values here. Then we need to measure the length of the shaft, which is between the two bearing, between the length of the two bearing, which is around 40 centimeter or 400 millimeter. See that the length of the shaft now it studies 40 centimeter or 400 millimeter. The shaft is subdivided into 8 sections, each of 50 millimeter, which is marked by some symbols or lines. Now, if we increase the RPM, the motion will transfer to the shaft and it will rotate. But before that, we need to clamp the knob tightly for our safety measures. Then we need to provide the speed. Whenever we increase the RPM, shaft rotates. Unfortunately, we can't take readings from the revolution machine. We need to measure the RPM from a tachometer. Another tachometer are used here to measure the rotational motion of the shaft. So in RPM, we'll take measures at the critical speed when it occurs. There are three conditions in the experiment. First condition, the mass are kept together but not at the center position of the shaft. So the mass will kept at the off-centered position of the shaft. We need to clamp that by seeing the marking here of the X section. We adjust the mass so that we can easily find the values of the A and B, and we also clamp the guide van here, protect ourselves from accident occurs. And actually there are some provisions or clearance between the shaft and the guide van. The shaft, as the shaft moves through the guide vans, there are certain clearance between the guide van and the shaft, so that the shaft doesn't touch it, which will, if the shaft touch the guide van, then it will hamper the deflection or rotation of the shaft. So it doesn't touch. There is some sort of clearance there. Let's take the readings of the first case when the mass is together but not at the center position. We're increasing the speed of the shaft now. For the first case, we'll take the reading of the tachometer just when the deflections are maximized or the higher deflections are found. As the vibration occurs, and once when we take the reading of the critical speed, we eventually reduce the speed to a zero value. We don't keep the shaft with the mass at the critical speed for a long time. Then we are taking the second reading for the same case so that we can average our values of the critical speed of the shaft. These are experimental value. We will compare these values with the equations provided in the lab sheet. There's some sort of vibration there. You can see. Okay, the third reading for the same case. The vibration occurs. Now these values of the motion are taken, and eventually the speed is moved to zero. We don't keep the shaft at this critical speed for a long time. Now the second case, where the masses are put together but at the center position of the shaft. We need to move the clamp through. The clamps are put at a distance of 5 centimeter of the mass. We avoid the larger deflection of the shaft. Actually, to avoid the accident, just clamp, tighten the knob. Every time we'll have to ensure that the knobs are tightened sufficiently. Then for the second case, we're taking reading now. We're increasing the speed. The laser should be put on the laser vibration occurs. We take the reading of this. We need to put the laser beam on the mass, not at the middle point, but on the surface of the mass. Second reading is taken. It's taken now. The vibration. See the vibration here. Let's listen the vibration. Vibration occurs at this speed, and we measure the speed, and eventually we reduce the speed to zero. readings. The vibration is happening. Just measure the speed. We'll take the average of these three values so that we can minimize our error, experimental error here. The third case, the masses are kept alone at the two position of the shaft, different position, the two different position of the shaft. This time the masses are not put together. They will put separately. So in this case, there are 2 point loads you can consider on the shaft. So we will also find two modes of vibration here. For this type of vibration, you need to calculate the critical speed using the Dunkerley's formula. Hope you all know the formula. We need to measure the critical speed of the 2 point load separately, and then we need to calculate the overall critical speed of the shaft. But as the masses are same here, 1 kg each, so the individual critical speed will be the same for two masses. So we just measure the vibration of one mass, and then calculate the critical speed of the shaft. In this case, the vibrations are severe than the previous two, so we need the help of our lab technician Abbas Bhai, so that he can hold the setup. As the first vibration is taken. There are two modes of vibration for each. For each run, we will find two critical speed. Whenever we increase the speed from the initial one, and now the second modes of vibration are found. And increasing the values to find the second modes of vibration. Now this is vibrating. See that it is vibrating. This is mistaken. The vibration can also be found from the setup. The setup and both the tables vibrated usually. Second reading. It's taking now. Initially, we will get a, let's see the vibration here. The lower speed will found a vibration critical speed, and whenever I increase further, we'll found the second critical speed. So what do you think? What is the importance to measure such critical speed of the shaft? In the practical field, we just want to avoid the situation of higher vibration or higher deflection of the shaft. So if we can know the critical speed of the shaft, we just avoid this higher vibration, larger deflection of the shaft. By just avoiding the certain speed. Otherwise, if we don't take precautionary actions, this critical speed, any accident can occur. This is our last reading. We have the first vibrations found. We need to be very much careful to measure the speed, because if we just increase the speed, the vibration will neutralize. And now we are further increasing from that speed. We're increasing speed from the first critical speed. Let's see the vibration of the shaft. The second also vibration of second critical speed. This is all for this experiment.